going to talk about an example of using radioactive decay, a very classic example of dating something by how much of a radioactive element it has. So let's say a sample of rock. We figured out somehow, and that's a subtle issue how you figured it out, but it contains 78% of the uranium-238 that it did originally. And we know the half-life of uranium-238 is 4.5 billion years, and we want to find the age of the sample. So there's a couple ways to do this. Probably the most direct way is to write down the equation for radioactive decay in terms of the half-life directly. So you take a certain amount, A naught, the original amount, and then you multiply it by 1/2 repeatedly. Well, how many times should you multiply it by 1/2? You take the time, and you figure out how many half-lives it is. So this is related to the earlier video about radioactive decay. So if the half-life is L, then this is one way to express the equation. So you convert T into half-lives, basically. You count how many half-lives. Then you multiply by 1/2 repeatedly, and that's the amount. Okay, so using that equation, we don't know A naught, but we know that what we have now is 78% of A naught. So 0.78 A naught is equal to A naught times 1/2 to the T, power, T over L, and I could write 4.5 billion right now, but I'm going to wait because there's no real point yet, and it's kind of messy. Okay, so the A naughts cancel, and so we just need 0.78 equals 1/2 to the T over L. And now here's where we want to take logs. Now if we wanted to, we could take the log base 1/2, and you can actually do that directly on the new version of the TI by the log base command. It's in the math menu, I think. But we can just take the log with respect to anything. And why don't we just take the natural log, because that's cooler, because cool people use natural logs. So ln 0.78 equals ln of this whole thing. And then we use rules of logs, because they're cool too. Okay, so that's equal to, the power comes down in front, and we get, not too surprisingly, in this business, ln of 1/2 and ln of 2 are just super, super important things. Okay, and so let's see, ln of 0.78, let's just go ahead and calculate that. So that is minus 0.24846. Notice it's negative because this is a number between 0 and 1. To get a number that's less than 1, you need fractions, or in other words, you need negative exponents. And then this is T over L. And then ln of 1/2 happens to be minus 0.6931. Okay. And I'll put in L in a minute, but let's just go ahead and isolate T. So T is just going to be L multiplied by L times the ratio of these guys, and the minus signs are going to cancel. 46 over 0.6931, and that, and let's put in L now. So that's 4.5, and this is going to be in billions of years. And let's just get it to calculate that. And so it turns out to be 1.613, and I don't really deserve any more decimal places because I only used 4 significant figures there. Billion years. Okay. So that's a pretty good way to do it. The only reason I want to show you a method too is that often you're going to be given something in terms of an E base. Now I kind of secretly used an E base here, and so these numbers are going to be pretty similar in method 2. But often you see it written out as A of T equals A naught e to the minus KT. Especially when we get to calculus, the E base is just absolutely dominant. There's really good reasons to do that to the exclusion of almost anything else. The trouble is that they're not telling us K, they're telling us L. So we need to remember how those are related, and then we'll be able to do the problem. So just a real quick review. The half-life means that the decay factor, notice this guy is the decay factor, it's the amount by which it decays. When the decay factor is 1/2, that's when T is equal to L. Okay, so let's solve that for K. So we take ln of both sides, and surprise, surprise, we get ln of 1/2 again. Ln of 1/2 equals minus KL. See, here, the base is E, and so we take ln. It really just strips off the E. ln of e to the something is just the exponent. And so K is minus ln of 1/2, and I'm going to simplify that a little bit, divided by L. And ln of 1/2 is ln of 2 to the minus 1. Let me just change it in place there. And then if you can take that out with rules of logs, and so you get ln 2 over L. That's a very, very, very common thing. When you're talking about doubling times or half-lives, this ln 2 divided by something comes up over and over again. It's related to what's called the rule of 70 for financial calculations, which we talked about. Okay, so in other words, we can actually get the K here, ln 2 divided by, and I'm going to do everything in billions of years because I don't want to put the billions everywhere, so just let's remember the units are billions of years. And so we'll just evaluate that numerically. And we get 0.154. That's good enough accuracy, I think. So our equation, so this is still just preliminary work, but it can be very useful if you're talking with somebody who really wants it in this form. And especially if you want to start doing calculus calculations with this. And I'm just going to remind myself that T is in billions of years. Okay. Now we're ready to go. Start a new thing. So now we go back to 0.78 A naught. Now we're not talking about 1/2. We're talking about 0.78. 0.7 A naught is A naught times e to the minus 0.154t. Okay. And so 0.78 equals just the e part. We're just canceling out the A naughts. And I take the ln of both sides. And the nice thing here is that it really, again, just strips it off. And so T is just going to be ln 0.78 divided by minus 0.154. And that, let's see, well, does it give us the same answer? Yeah, 1.613. And that gives us 1.613. Oops. And again, billion years. So by putting the T in the right units, I didn't ever have to put in like 10 to the 9ths or like incredible things with lots of zeros and stuff like that. So that's two ways of doing it. Method 1 is more direct, but method 2 gets us this very nice auxiliary thing, which is really a better equation in a lot of ways for the general radioactive decay. If you were going to do a bunch of problems about this, it'd be good to put it in this form first, and then you do a bunch of analysis with different scenarios.